welcome to our first installment for object-oriented programming, getting the design right to get the most out of frameworks. To some extent or another, every object-oriented design should try to achieve flexibility, adaptability, modularity, reusability, scalability, quality, and security. Now, depending on what your goals are for your application, you will have different emphasis on different parts of these abilities that are listed. Probably, though, I think the most important one is going to be flexibility. Without flexibility, you're going to have a hard time dealing with changes in requirements, and changes in requirements are inevitable. So we have to look forward to being able to work around a very flexible design. That kind of goes hand in hand with adaptability, being able to adapt your design to other similar types of applications. Now, the bottom line to all of this is modularity. Modularity is really what enables us to be able to reuse components, to be able to adapt components to different things. Modularity means we have low coupling, low interdependence between objects, and that also means that you would have a very high cohesion within your modules themselves or classes. Reusability is always a goal. Scalability, that might not be an issue for your application. Scalability simply means that we can distribute your application over multiple servers to increase the number of users that it can accommodate. We always want quality, and of course, we want applications that are secure. Now, over the last few years, we've seen a lot of new language features show up. Whether you're programming in Java or C++ or C#, we've seen over the last few years Lambda expressions show up. This is to support the idea of functional programming, starting with C++ version 11, the introduction of functors, starting in Java version 8, functional interfaces. And C# has had delegates for quite a while, as well as Lambda expressions. These are all concepts to support functional programming. This enables a lot more leverage for frameworks and supports the idea of inversion of control, as well as dependency inversion. Frameworks are also becoming more supportive of functional programming as well. We see this in the most recent editions of the Java library, the JDK, as well as the C++ version 11 standard library, which is much more framework oriented, much more supportive of functional programming. And the .NET framework always pretty supportive of functional programming, but the newer .NET Core library is very functionally oriented. This leads to something else as well that we call declarative programming. The language integrated query or LINQ in the .NET libraries, algorithms headers in C++, and the streams, these are all supportive of declarative programming and what we sometimes call fluent interfaces. Now, why have all these new language features? It's in response to the kinds of designs that designers are trying to achieve. Design concepts that have been around for a long time, but were maybe not so conducive in the languages to elegantly implement these great designs. So to give you a reminder of what we're trying to do when we create a great design, let's take a look at an acronym called SOLID. Within SOLID, we will have single responsibility. The O stands for the open-close principle, which means that we're open for business, so we're closed to modification. We're open to extension, but we're closed to modification. In other words, don't modify your code in a way that would break other code that other programmers would be responsible for. Liskop's substitution principle. Substitution is the key here, and this is one of our most key goals in a great design is substitutability. Interface segregation. This means splitting interfaces up based on the caller or the user of the interface. And finally, dependency inversion. The last three principles really are trying to support the concept of substitutability. Now, today we're going to focus in on single responsibility. We'll cover the other SOLID acronym letters in future videos. Now, when we're trying to achieve these solid goals, one of the things that naturally will happen is we're going to run into other barriers or obstacles in our design effort. Design patterns are common solutions to those common problems. Design patterns maximize or leverage inheritance, interfaces, polymorphism, and inversion of control. All right, let's deep dive into single responsibility. And single responsibility, the S in SOLID, means that a class should be cohesive. That means it should have high internal dependency, that the class methods would use one another, and that the class methods would use most of the fields, instance variables, defined within the class. a class should only have one reason to change. This is Martin's description of single responsibility. And what does that really mean? It kind of means that in terms of specifications, if something changes in your requirements, would that affect a change to your class? If there were two different requirements that might change, would both of those have an impact on your class? Single responsibility means that there would only be one requirement that would cause or impact a change on your class. We have to be careful about how we conceive that definition, however. Say, for instance, that you're building an application for selling used cars. Like, say, a company like CarMax or somebody wanted you to build an application for them. Now, this application is going to support the consumer-facing web application as well as internal management and sales. One of the obvious classes that you might come up with would be vehicle. What kind of attributes and what kind of functions would that class have? Remember, this is for a used car application, not a car simulator or onboard software. So to support the inventory system as well as the website browsing for cars, we might create a class that looks something like this. A vehicle has a make, model, trim, year, manufacturer's suggested retail price, a VIN number, miles, condition, color, gross weight, price, and cost. These are just the attributes. We can talk about what other functions or methods we would put in that class in a different effort. Now, this looks like a perfectly reasonable object-oriented design. We're mimicking a real-world vehicle, and immediately you would discover that a lot of your objects have identical data in some of the fields. In particular, looking at this list, a lot of your used vehicles are going to be the same make, model, trim, year, and therefore manufacturer's suggested retail, as well as the gross weight. So the ones that I've dimmed out here, those are fields that describe a classification of vehicle, not individual used cars. In other words, all 2015 Jeep Cherokee Summits would be the same make, model, trim, year, MSRP, and gross weight. The VIN number, miles, condition, color, and cost all relate to a specific used vehicle. So really there's a mixture of two different concepts within this same class. There are two reasons that our vehicle class could have to change. If there was a change in how we interact with the manufacturer's web services to retrieve some of that information, that would cause a change to our class. If there was a change to the requirements on how the information for a specific car is viewed by consumers or browsed by consumers, like for instance adding pictures of the car, that would also be a reason to change or rewrite part of our class. Two very distinct and different areas of requirements for our application. This is a very common design flaw, where the specification of a category of objects is confused with the data of the objects themselves. A better design would split this into two classes. One class would contain the common information about make and model. The other class would contain information about a specific used vehicle. So in this case, we're going to split this up and have a class called vehicle, which eliminates those common fields and just has the specific values. We're also going to have another class called vehicle spec, which contains the common information, make, model, trim, year. This also creates a one-to-many relationship. The asterisk in the UML here indicates that there are many vehicles per vehicle spec. The line that connects our classes also does not have an arrowhead on either end, indicating that this is a bidirectional relationship. There is a field inside a vehicle that references the vehicle spec object. Likewise, the vehicle spec has a collection of vehicles that meet that specification. Does this need to be bidirectional or one-directional? That really depends on other requirements within the application beyond the scope of this particular discussion. As we move through these series of videos, though, we'll touch on all of the other design aspects. And this all comes together to gel, to create a great design. We want to create great designs. We want to code happy. Don't forget, press that subscribe button so you don't miss any future videos. I'm Chuck McCullough. Have a great day.